And welcome Calculus 3 students. Today we are looking at surface integrals. This concept is if you can think of trying to find the average temperature of the Earth, and we are thinking about it as a surface and it's colder at the poles, and we know the temperature distribution and a function associated with that. How can we get that average temperature? And that's what we're doing today. So we're going to be looking at different shapes, and we're going to write our functions in terms of parameters. First up, we will, sometimes it would be most convenient to write things in terms of cylindrical coordinates. Notice here the conical coordinates. We could write our parameters in terms of cones. Spherical coordinates, we can write our parameters in terms of spherical coordinates. So as you notice, there's many different ways to write our functions in terms of other parameters, and so we'll have to make a determination of how we're going to define our function, what type of parameter we're going to use, whether that be spherical, conical, or cylindrical. This first one, we're just going to write it in terms of straight up parameters just because it's plain and it would just be easier. So if I just go ahead and let u equal to x and v equal to y, that would then mean that my z, solving for z, would then be the 2 and then move everything over. That would be 3u plus 2v, and in terms of parameters, my r, in terms of parameters u and v, I would then have the vector u, v, and then this 2 minus 3u plus 2v, where u and v range from positive infinity to negative infinity. Now, noticing this thing, I think I'd like to go to polar coordinates, in which case I'm going to let u equal to theta, and v, you can either choose v to be square root of z, or you can say that, v equals z. I kind of like v equals square root of z. That way I'm totally in polar coordinates. This would mean that z is equal to v squared. So I'm going to have that x squared plus y squared is equal to v squared. And I can now say that x equals v cosine theta. I can say that y equals v sine theta. And writing this in terms of my vector r with a u and a v, I will get my I component to be v cosine u, and I would get my j component to be v sine u, and that third component would then just be v squared. Now if I do this, that would mean, since u is theta, u is going to vary in between 0 and 2 pi, obviously. And our v, because this is our limitation on z, that would mean that our v then varies between 0 and 3. We are now finding the surface area for the following surfaces, and we're going to be using our definition as above. First up, we have a cylinder of radius a, and it has to be something that actually exists, so it's greater than 0. And if you'll look back, you'll see that in terms of u and v, this vector r would look like a cosine u, a sine u, and v. So that would be our cylinder. And this would be with my u varying between 0 and 2 2 pi, and my v varying between 0 and h. So we'll write that down. Alright, next up we need to find our normal vector, and let's write down what that definition is with that cross product, and it's a lot neater than I can write it. So what we will do next is for our I, j, and k components, we will take the partial of this x with respect to u, and then we'll place it here, and then we'll take the partial of this y component with respect to u, place it there, and then we'll take, so anyway, that's by definition, so let's write that down. Alright, after those partials are complete, here's what they look like, and when you find the determinant, you will end up with the following vector. If we look at our surface integral here, notice that I need to find the magnitude of that vector. The magnitude of that vector, I will just take the square root of the a cosine u quantity squared, and that magnitude I will end up with looks like this, and this is all just getting set up to do my surface integral. Let's notice from our definition that our f with x, y, and z, f of x, y, and z, if it's 1, then the integral equals that surface area. So let's get our integral set up. Here's our integral, 1 ds. In our case, we're in our rectangular coordinates, and we've got rectangular. This is going to be this magnitude of this guy right here, and let's just go ahead and I'll go ahead and write it du cross tv, and integrate that with respect to area. So I'm going to have 0 2 pi 0 h a dv du, and solving that integral you will get 2 pi a h, which happens to be the surface area of a cylinder, not including the ends. Next up, they want me to do this for a sphere of radius a. If I go back to the very beginning where they told me parametrically what this sphere would look like, I'm going to use this. So here we have the sphere parameterized, and this is how my u and v would vary. I need to get actually the magnitude of this normal vector, but getting the normal vector, I will follow this definition as it's sitting right here, and I will take the partial of each one of these components with respect to the u and the v, and when I compute that, I will get the following vector. And when you go through and get the magnitude of your normal vector, what you're going to end up with is a squared sine u, and we are then going to define our integral from 0 to 2 pi, 0 to 2 pi, and it is going to be my magnitude, which is the a squared sine u du dv, and computing this integral you will get 4 pi a squared, which is the formula for the surface area of a sphere, amazingly enough. In our next example, we have to figure the problem out first, and we have a cylinder, and this cylinder has a radius of 4 and goes all the way around 0 to 2 pi, but we have sliced off here at the z equals 0 line, and then we sliced off a piece of it along this line, along this plane, z equals 16 minus 2x. Well, getting the parameters of the cylinder looks like this, where u is theta and v is z, but now the hard part is figuring out, so how am I going to get the region of integration? Well, I note that z equals 16 minus 2x, and I know that x is this 4 cosine u. So I'll just substitute that in. I'll say 16 minus 2 times 4 cosine u. And once I do that, I will get that this is 16 minus 8 cosine u. And I know that v equals z, so this is going to be my v. That means, and you can note here, u varies between 0 and 2 pi, and v varies between 0 and 16 minus 8 cosine u. So putting this all together, from 2a, we had that the magnitude of that normal vector was equal to a, so in this case our a is 4, and our surface integral then will look like such, and we will then integrate, and integrating this thing you'll get 128 pi. And that's it for example 3. Alright, on this one we are looking at the average temperature on a sphere. So we are going to parameterize this on a sphere, and we will go ahead and write down what that looks like. So here we go. We have that the parametric description of a sphere with u equal to phi and v equal to theta then becomes our function in terms of u and b, this 10 plus 50 sine u. And we know that the magnitude of our normal vector is a squared sine u because we found that earlier. So now we can just plug in to our integral. And when we do that, it's just a straight up integral. Note how my phi and theta, they vary between 0 and 2 pi and 0 and pi. And just integrating that integral, this is what we'll get. And then for our particular problem where we have temperature 10 degree at the pole and 60 degree at the equator, means that we're going to have to take our 10 pi a squared 4 plus 5 pi and divide it, because we're wanting the average, so we're going to divide it by the surface area, which is 4 pi a squared, something we found earlier. And we're finding the average temperature, so we'll do this, and when we compute this we will get that it is 20 plus 25 pi over 2. In other words, that temperature is 49.3 degrees. Right, and setting this one up, we're going to need to know, notice how this is our evaluation of surface integrals for our scalar valued function. So this is what we have. We're going to need to know the partial of our z with respect to x, and so I'm going to have this surface integral where my function is 1, and in this region I will have the partial with respect to x. This is a minus 4, so I want the minus 4 quantity squared, plus the partial with respect to y. This is going to be minus 3 quantity squared plus 1, and then that's dA. This is then going to get me square root of 16 and 9, add 1 is 26 dA. So we just have this double integral, and it is just going to be the area of the region bounded by the ellipse, and we know what our axes of our ellipse is, so we can compute that area of just a plain ellipse. So let's write that down. Okay, here's our ellipse. Notice that I have my axes of length 2 and 1. There's the area of my ellipse, so for the area of my surface, it's just going to be this square root of 26 times that area of the ellipse, which is 2 pi, so we'll just write 2 pi 26, and that is our surface area. All right, we have this cone that is denser at the bottom than it is at the top, and we're supposed to find the mass of the cone. Well, first we're going to need to know what this projection is here onto this XY plane. Well, here's our z function. That means that our z goes at maximum at 4. That means that x squared plus y squared equals 16, and that is going to be our disk, or our projection onto that XY plane. So there's a few other pieces of information that we're going to need to know here. We're going to have to find, because we're looking to do this double integral, this x, y, z, which is our density, and then we're going to need to know the partial, once again, of z with respect to x, and y add 1, and this will be over that region. This is just this density here, this 8 minus z. Next, what we're going to need to do is do a little bit of algebra to get our get what this quantity here equals. So we're going to use the fact that our z is equal to this. In other words, z squared is x squared plus y squared. That's going to make it a little bit easier. And let's write down the algebra for that. Alright, that algebra looks somewhat like this. You'll see that since we know that x squared plus y squared is the same thing as z squared, I can say that that's 1. After taking these partials, that makes it handy. And in writing this integral down, I'll just snip that. Just going through that integral here, just substituting for what I wrote down to begin with, you'll see that you end up with this 379 grams. Here's a nice little summary. I would have this available when you go to take your test. This is very handy. It just writes down all the parametric equivalencies, also gives you that normal vector, which is very handy to have. Alright, we have a vector field 0, 0, negative 1 corresponding to a downward flow, and it's along this plane, the 4 minus 2x minus y, only in this first octant here. Alright, what I'm going to need to know, one of the first things is I'm going to need to know the partial of z with respect to x. That's going to be minus 2. The partial of z with respect to y, that's going to be minus 1. And then my normal vector is then going to be that cross product of that TU/TV, and that's with taking all of these partials. Now this would give us that vector that's normal to the plane is going to be this negative my z with respect to x, and then negative my z with respect to y, and then that 1, and this is going to then equal 2, 1, 1, and due to this force right here and this plane here. Now this is going to point upward, and we're interested in the downward flux, so we need this in the negative z direction. So our normal that we're going to be looking at is then negative 2, negative 1, negative 1. So, alright, so here's going to be our integral. It's going to be this double integral, and the dot product with my n ds, bring this into this r. We're going to need this dot product of the 0, 0, negative 1 dotted with negative 2, -1, -1, integrated with respect to the area. And this is going to then just be that area of that region. Now the base R is a triangle in that XY plane. Notice it here with its vertices at the 0, 0, at 2, 0, and at 0, 4. And the downward flux across S then is 4 because this area is then 4. So if I mark these points here and I just do the 1/2 the base times the height, I'll find that this area is then 4. In example 8, we're going to find that the base of both surfaces in the XY plane is this unit disk R that has the form and the projection into that XY plane of x plus y squared. So it's a circle of radius 1, and this is in polar coordinates going to be that my R is in between because it's of radius 1, between 0 and 1, and my theta is going to be, of course, in between 0 and 2 pi. And seeing as we have x squared plus y squared plus z squared equals 1, implicitly we can say that zx is equal to negative x over z, and zy is going to be equal to negative y over z. Therefore, our normal vector is then going to be equal to this x over z, x over z, y, z, and then a 1 for that z component. So in integrating, we're going to have that our vector field dotted with our normal is going to be equal to this negative f zx minus g zy plus h integrated over that region. And in terms of area, we're going to do our substitutions here, and we will get our double integral, and then it would be x times x over z plus y times y over z plus z dA. Alright, now I'm going to fill in that integral for our limits of integration and in terms of polar coordinates. And this is the integral completed in its entirety, and you'll get 2 pi for that one. And we're so lucky because this was 2 problems in one, and in our next problem we have to do it for the paraboloid. So let's do the other one, and then we're going to see, I think we're supposed to figure out which one was greater, which is the upward flux greater across the hemisphere of this, the one that we just did, which was 2 pi, or the paraboloid. So we'll do that one. Alright, this video is getting long. So for the paraboloid, here is our function, here is our parametric description that we found in 1b, and with the limits on u and v, where u goes from 0 to 2 pi and v goes from 0 to 1. And then there is the normal vector here and its calculation. Once again, this normal is in the opposite direction that we're looking for, so our normal then needs to be 2v squared cosine u and 2v squared sine u and then minus v. I'll fix that.